Well, hello everyone, and welcome back. In this video, we will continue where we left off, discussing AC power. Here we will discuss the power factor and maximum power transfer for AC circuits. If you haven't already done so, please make sure you've reviewed our previous video introducing complex power. Here's our goals for today's video. First, we're going to take a closer look at complex power, which we learned about last time. And we're going to take a close look at the physical significance of each term in our complex power. We will also understand the physical significance of the power factor. Next, we will see how we can apply the power factor in order to efficiently transfer as much power as possible between a source and a load. And finally, we will revisit the maximum power transfer theorem, and we'll see that in AC circuits, the maximum power transfer theorem is very similar to what we learned in DC circuits. There are a few differences that we'll want to pay attention to. Let's first start with a brief review of what we covered last time. You'll remember that AC power actually can come in a variety of flavors. First, we have our instantaneous power, which is our AC power as a function of time. We can write our power as a product of current times voltage, but because of that trig identity that we learned about last time, the product will actually result in our instantaneous power equation. And you'll remember that we have this time-independent average power plus we have a time-dependent term with double the frequency. So the instantaneous power is the sum of some average power term plus a time-dependent term. So therefore, if we take the non-time dependent part of our instantaneous power, that will give us our average power, which is the average power that we were able to deliver over a complete period of our AC signal. If we want, we can also calculate average power delivered to an element with impedance Z. And you'll remember, because of the trig identities, we end up getting this factor of 1/2 that pops out. And so our average power delivered to some circuit element will be our current magnitude squared divided by 2 times the real part of our impedance. Notice in all of these cases, our units for power will be watts. Definitely keep these equations handy if you haven't already written them down somewhere. These are very helpful to have in front of you as you work on our homework assignments and other practice problems. Last time we also introduced this thing called the complex power. If we want to write our AC power in frequency domain, we write it as complex power S. So this allows us to represent our AC power in terms of current and voltage phasors. This first equation here is very important. Please make sure you remember this one. You'll probably need it on the final exam and on our upcoming assignments. So if we take our voltage phasor times the complex conjugate of our current phasor, remember the star here means complex conjugate, take our voltage phasor times complex conjugate of current divided by 2, and we will end up with our complex power. Just like the other numbers we have talked about, since complex power is a complex number, it can be written both in polar form and in rectangular form. And units for complex power are called volt-amperes. We'll take a closer look today at these other terms that appear in complex power. So that includes our average power P, or the real part of complex power. We have reactive power Q, which is the imaginary part of complex power when written in rectangular form. We also have our magnitude of the complex power when we write it in polar form. That's known as the apparent power. And finally, we get this power factor angle, which is the phase angle of the complex power. So in today's video, we'll take a closer look at the physical significance of each of these terms. Please keep these equations very handy because you're going to need them in the rest of the course. So before we move on, let's do a quick practice problem about complex power. So here we have a basic RL circuit, and we're asked to find the complex power delivered to the load. So here, for the purpose of this problem, we're treating our source as that voltage source and the load as the combined resistor and inductor. It's a good practice whenever you solve problems like this with sources and loads. Make sure you pay attention to which thing you actually want to find complex power across. So this is a very good thing to watch out for because in this case, our voltage and our current will be the same as the voltage and current from the source, but that is not always true. For example, if I only wanted to find complex power delivered to my resistor here, then the voltage phasor that I plug in would not be the same as the source's voltage phasor. So again, just writing out our caution here, what we're saying is that the voltage and current that we plug into our equation, it's not always going to be the current and voltage exiting the source. The thing you want to plug in is the current and voltage through the component of interest. So please keep this in mind, especially as you're working on other homework problems. For the case of this problem, we do plug in the voltage and current that are exiting the source, because that is the voltage and current that our load sees. But we'll do some other examples later where the voltage and current we plug in for complex power are not the same as the voltage and current through our source. So just something to watch out for. So let's go ahead and give this question a try. We're being asked to find the complex power delivered to the load, where the load is our inductor and our resistor. We are also given that our load has a 9 ohm resistor and a 5 Henry inductor, and we know the sinusoid for our source. Let's first transform to frequency domain. And so if we transform to frequency domain, let's see what we get. Our voltage source becomes 24 angle 75 degrees. Our 9 ohm resistor just becomes a 9 ohm impedance. And for that inductor, the impedance is just given by j omega L. In this case, notice we know our omega is 3, and our L is 5 henries, so we get j times omega is 3 times L is 5 henries, which gives us j15 ohms. So therefore we can simplify this circuit one more time. And in this case, we can combine our resistor and inductor together, and we get a 9 plus j15 ohm impedance next to our 24 angle 75 degree source. We can also write 9 plus 15j, we can write that complex number in polar form as 17.5 angle 59 degrees. All right, so now our circuit is in frequency domain, and our goal is to find complex power. Let's remind ourselves of our equation that we need for complex power. So to find complex power, we use the equation S equals VI star over 2, where V is the voltage delivered to the load, or the voltage across the load. In this case, this is a phasor. And remember, I star is a complex conjugate of the current phasor. And remember, since we want the complex power delivered to the load, this will be complex conjugate of current phasor, where that's the current across the load. All right, so in this case, we need to find our voltage V and our current I passing through our load in order to find complex power. Well, how would we find our current I? In this case, it just becomes a simple Ohm's law problem. So here's our strategy. Let's find first our current I through the circuit. And in this case, to find I, we can just use Ohm's law using V equals IZ. And then we can use that current I to get V load. Or in this case, since our load is the only thing in series with our voltage, we can recognize, in this case, V load is the same as the voltage from our source. So let's go ahead and first find our current I. So in this case, we know by Ohm's law, we know our current I must be equal to our voltage phasor across the load divided by Z, which is 24 angle 75 degrees volts divided by 17.5 angle 59 degrees ohms. Remember the 17.5 angle 59, that was our equivalent impedance in polar form. So we go ahead and solve for I, and we determine our current I must be equal to 1.37 angle 16 degrees amperes. And again, as we mentioned, in this case, we can see that our voltage V for the load must be equal to the voltage across our source. So we'll use voltage V is 24 angle 75 degrees volts. Now we're ready to plug in and find our complex power. So in this case, we go ahead and substitute. So we have, for voltage V, we have 24 angle 75 degrees. Remember, for current, we have to take the complex conjugate. So our current will be 1.37 angle negative 16 degrees amperes. So remember to take the complex conjugate. And divide by 2. Some people prefer to divide by 2 angle 0 degrees. That also works, because you're just dividing by a real number. So in this case, if we go ahead and perform that math, we will determine that our complex power S will be 16.64 angle 59 degrees volt amperes, or in rectangular form, if we use our phasor calculator, we will determine in rectangular form that gives us 8.47 plus J 14.1 volt amperes. And there's our answer. There's one more point worth mentioning for this particular question. Suppose you had a homework question where you know the complex power, but you do not know the resistance and inductance. So in this case, if you know the voltage source V and you know S, but R and L are unknown, you can still solve the problem. In this case, you would first use S equals VI star over 2 to determine I using the known S and V, and then use V equals IZ to determine the load impedance Z. And then if you know the impedance is given by an inductor plus a resistor, then you know that the Z value that you get must equal R plus J omega L. You can compare coefficients to find the R and L values. So you might also see problems on the homework or in our textbook where you know the complex power, but you don't know the identity of the load. And as you can see, you can basically approach this problem in reverse in order to determine the unknown load. All right, so hopefully you found this example helpful. And if you'd like additional review, please do take a moment to go back and check out our previous video on complex power. Let's now move on to the physical significance of the complex power terms, and then we'll talk about power factor and maximum power transfer. So our first topic for today was reviewing the physical significance of our complex power. You remember from our toolbox, we have this nice equation for complex power. We know that our complex power is given in rectangular form by P plus JQ, or in polar form by our apparent power S angle theta. So S is our apparent power, or the magnitude of the complex power. You can see in this phasor diagram, it's basically the hypotenuse of the triangle, or basically the magnitude of the complex power phasor in polar form. Next we have P. P is the real power, or the real component of complex power. This is the power that we can actually use. So we generally want the P value to be as high as possible. Next we have Q, which is the reactive power. And Q is the imaginary component of the complex power. Most of the time we are unable to use that imaginary component, so generally we want to minimize the Q value. And finally we have theta, our power factor angle. Sometimes this is also called the load impedance angle. So let's take a closer look at each of these and see why we should care about them. So first is our apparent power. And that's our magnitude of the complex power. And we call it the apparent power because this is a value we would actually measure if we were using RMS and an AC power meter. That's why we call it apparent. This is the value that we see. The real power P is very important. The real power P is the real or true power available to do useful work. And we'll see that this is actually equal to the average power. If we look back at our instantaneous power equation, this real power P is the same P as the average power in that instantaneous power equation. So this is the average power that a purely resistive load would feel. So most of the time, since P is the useful power available to us, usually we want to maximize P. And notice that this P value will be maximum when our phase angle theta is equal to 0. Another application where this becomes important is in electrical utility companies. It turns out that an electric company delivers the total complex power S to your home, but electric companies can only charge you for P, the power that you consume. So especially if you are an electric utility company, you really want to maximize the real power P because you can't get paid money for the reactive power Q. Next is our reactive power Q. Remember, Q is the imaginary component of the complex power in rectangular form. Most of the time, we want to minimize that reactive power Q because most of the time we just can't use it. It's imaginary. And as we mentioned before, the electric utility company can only charge customers for the real power P. So most of the time we are trying to minimize this reactive power Q. And notice that if theta is equal to 0, then our reactive power Q will be equal to 0, and our real power P will be maximum. Finally, that brings us to our last quantity here, which is the power factor angle, or theta. This power factor angle theta is really important because it basically determines how much of our power is real versus imaginary. So you can see based on our phasor diagram that the amount of real and reactive power we get depends very heavily on the cosine of theta v minus theta I. This quantity is so important that we call it the power factor. This is very important. So please remember, power factor is given by cosine of our voltage phase angle minus our current phase angle. So let's take a closer look at this power factor. As we mentioned, power factor is the cosine of theta v minus theta I. So power factor is always going to be some value between 0 and 1, because theta v minus theta I will generally always produce the cosine between 0 and 1. And so notice that essentially what this tells us is it tells us how much real power versus imaginary power we're going to get. Notice if our power factor is equal to 1, that means that we have maximum efficiency of power transfer because our power will be 100% real. And imaginary power will be 0. If our power factor is equal to 1. On the other hand, if our power factor is equal to 0, then our power will be completely imaginary. And we'll see in just a moment that the power factor is actually something that we can correct. So if our power factor is somewhere between 0 and 1, we can actually add a capacitor to make our power factor potentially go higher and become closer to 1. Let's do a quick practice. Let's take a moment to determine the power factor for each of these circuits. First, let's remind ourselves that the power factor is given by cosine of theta v minus theta I. If you'd like, take a moment to pause the video and see if you can find the power factor for these two circuits. Otherwise, we'll do them together. So let's start with circuit A. From circuit A, you can see that theta v is 15 degrees, and the theta for our current, theta I, is 47 degrees. So in this case, for circuit A, our power factor is going to be equal to cosine of theta v minus theta I. So that's cosine of 15 degrees minus 47 degrees. So in this case, our power factor is equal to cosine of negative 32 degrees that will give us a power factor of 0.848. Let's try circuit B next. In circuit B, you can see that our voltage has a theta V of negative 15 degrees in this case. And you can see that our current phasor has a theta I of negative 22 degrees. Once again, we substitute into our power factor equation. Here we have cosine of negative 15 degrees minus negative 22 degrees. Be careful here. Notice we have minus negative, so that is the same as adding a positive. So 15 degrees minus negative 22 degrees, that gives us cosine of positive 7 degrees, which will be equal to 0.9925. Notice in this case, circuit B actually gives us the closer to ideal behavior. Alright, so based on what we discussed with power factor angle, you'll see that we actually end up with 3 possible cases for any given AC circuit. Our first case is our ideal case. If our theta value is equal to 0, we'll see that we call this our current being in phase with the voltage, because the phase angles between our voltage and current are the same. This is the ideal case, and we'll see that if current and voltage are in phase, our power factor will be 1 because our power will be completely real. That's our ideal case that we're aiming for. Unfortunately, most of the time, we can't always get perfectly ideal power factors. So sometimes we end up in case 2 or case 3. In case 2, you see our theta value is less than 0. So in this particular case, you see that our load gains capacitive behavior because the net behavior of the load produces a negative Q, which is similar to the behavior of a capacitor. And finally, for case 3, if our theta is greater than 0, we see that our power factor will still be less than 1, but the load will instead have inductive behavior. Notice that case 2 and case 3 correspond to the leading and lagging case. And you see in this figure, we see that our current is ahead of our voltage in time. And finally, we see that if our current phase angle is less than that of our voltage, then our current is lagging, and you can see that we get the lagging behavior. Alright, so let's take a closer look at each of these cases for the power factor angle. Our first case is the case when our power factor angle equals 0. As we mentioned, this is our desirable or ideal case. We say that the current is in phase with the voltage, and our load behaves like a purely resistive load. We see that the imaginary component of complex power, Q, is 0. We see that our voltage phase angle is equal to our current phase angle, and power factor is exactly equal to 1. So, while this is our ideal case, usually it's very challenging to reach this in the real world. So, usually achieving a power factor around 0.95 is feasible, but depending on our system, it may not be possible to achieve a perfect power factor of 1. In our second case, this is our leading case, where our voltage phase angle is less than the current phase angle. So again, we say that our current is leading the voltage, and our load is capacitive, meaning the net behavior is like that of a capacitor. In this case, because our voltage phase angle is less than the current phase angle, we end up with a negative Q value. So as shown in our phasor diagram, you see that the imaginary component is negative. One thing to note is that this case, the leading case, is less common in the real world, because usually our loads tend to have inductive or resistive behavior. It's less common for a load to have purely capacitive behavior. Finally, we have case 3. In this case, we see that our phase angle of complex power is greater than 0, and this corresponds to the lagging case because our voltage phase angle is greater than the current phase angle. We see in this case that our load has inductive behavior and our power factor is still less than 1. In this case, we also end up with a positive Q value, so positive reactive power. And this is actually our most common case. Often our loads have slightly inductive behavior. And the good thing about this case is that it is possible for us to improve the behavior. One thing we can do is we can place a capacitor in parallel with the load. If we introduce a parallel capacitor, that will introduce a negative Q, and that will cause our imaginary part to decrease and therefore make our power factor closer to 1. And again, typically in the real world, we often are able to raise our power factor up to about 0.95 using that approach. So just a reminder, when you are working with power factors, you always want to make sure that you remember to specify whether your power factor is leading or lagging. Remember, leading or lagging allows us to distinguish between case 2 and case 3. So it's very important whenever you report a power factor, you should always specify whether power factor is leading or lagging. So definitely make sure you remember the rules. We say we are lagging if our current phase angle is less than the voltage phase angle, and we say we are leading if the voltage phase angle is less than the current phase angle. Let's do another quick practice. Let's return to that circuit A from example 1. In example 1, we found that circuit A had a power factor of 0.848. We should always specify whether we are leading or lagging when we report our power factor values. So take a moment and see if you can identify, will this power factor be leading or lagging, and why? Let's go ahead and remind ourselves. It's very important that we remember our rules for leading versus lagging. So in this case, let's take a look at circuit A and see what we get. Notice here, we had calculated that theta V minus theta I is less than 0, and we see that theta V is less than theta I. So in this case, you see that we must indeed be leading. because we see that theta v is less than theta I, and we ended up with a negative power factor angle. So in this case, the correct way to report the power factor would be 0.848 leading. Let's try again with example 3. Now we're looking at circuit B. You'll remember for circuit B, we calculated that our power factor was 0.9925. So once again, let's take a look at our theta V and theta I and see what we get. Well, in this case, we see that theta V minus theta I is greater than 0. And we saw that theta V, even though it's negative, it's still greater than theta I. So in this case, since theta V is greater than theta I, this must be the lagging case. So we would say that our power factor is 0.9925 lagging in this case. So make sure you remember those rules. It's very important to be able to recognize whether we're leading or lagging in order to communicate the correct behavior. Let's do one last example before we move on. Suppose you have a circuit where you're told the power factor is 0.8 lagging. So in this case, we want to find the phase angle for the current. One thing to keep in mind, as noted here, is that our current phase angle is always measured relative to our voltage phase angle. So in this case, for problems like this, I recommend that you assume your voltage phase angle is 0, because you just need a reference point to compare your current phase angle to. Remember, your power factor can be used to determine the difference between your voltage and current phase angles. So we just need to assume a initial value for the voltage phase angle in order to find our current phase angle. So in this case, let's go ahead and assume our voltage phase angle is 0. We know our power factor is 0.8 lagging. Remember, 0.8 lagging, that tells us that in this case, theta V must be greater than theta I. So we need to remember that. So in this case, we can substitute what we know. So in this case, we know 0.8 must be equal to cosine theta V is 0 minus theta I, which is unknown. So we can say inverse cosine of 0.8 must equal 0 minus theta I. And notice here, inverse cosine of 0.8 could be either positive or negative 36.87. And remember, cosine is an even function, so inverse cosine 0.8 could be positive or negative 36.87. So in this case, we need to figure out, well, which is it? Notice we know theta V must be greater than theta I because we are lagging. So we're told theta V must be greater than theta I. And we know theta v here was 0, because we assumed that. That means, in this case, theta I must be less than 0. So theta I must be equal to negative 36.87 degrees in this case. So notice it's very important to pay attention to what the leading and lagging tell us in order to identify the correct phase angle at the end of our question. All right, so now let's briefly take a closer look at that idea of correcting power factor. We mentioned a moment ago that if we have an inductive load, we can add a parallel capacitor to our inductive load. So notice this allows us to reduce the phase angle of our complex power and improve the power factor. This increases the real component of our complex power and enables more efficient power transfer. Basically what this is doing is this is introducing some negative imaginary current, and it's offsetting some of that positive Q, or the reactive power. So you see that that parallel capacitor decreases our reactive power and increases our real power. So how do we actually perform this power factor correction? It turns out it's actually pretty easy to determine what capacitance you need in order to improve your power factor. I recommend you follow this recipe shown here. You'll see that all we need to do is first convert to frequency domain. We find the impedance of our load in rectangular form. We identify what we want to correct our power factor to, and then we use this equation to determine the imaginary part of our corrected impedance. One thing to note is this equation comes from trigonometry. I'm not going to derive the whole thing here, but if we were to do some trigonometry to figure out the change in theta required in order to produce the desired Q, you can actually do trigonometry on your phasors in the complex plane, and that is how we would end up with this corrected impedance equation. You can check out our textbook Circuit Analysis and Design for the full derivation if you're curious. Finally, notice what we can do. In the last part of the question, if we know this x1 term, then we can figure out, we know impedance of a capacitor is 1 over j omega c, so we can figure out what capacitance we need in order to produce that desired impedance. So let's go ahead and do an example showing this recipe in action. It's actually a fairly straightforward process. So in this example, we have a power company, and they want to use the circuit below to deliver power to a customer's load. We're told that the load has an impedance of 100 plus J100 ohms, and we want to correct the power factor to 0.95 lagging. We're also told to assume that we are operating at 377 radians per second. You'll notice in this case, our voltage is not given to us, and it's actually okay for the purpose of this question. First, we need to treat the circuit without the parallel capacitor and see what our original impedance is. And then we use our recipe to figure out what parallel capacitor we need. So let's give this a try. And for this question, I recommend that we follow our recipe. So our first step is to convert to frequency domain. And remember, in this case, we should assume the parallel capacitor is not added yet. And so if we do that, we have some voltage source. And notice in this case, we have our load, which is 100 plus J100 ohms. The second step of our recipe is to determine the impedance of the load to be corrected. And of course, in this case, we want the impedance in the form Z equals R plus JX. Well, for us, that was given. We know that our impedance here is just 100 plus J100. But sometimes, depending on the question you have, you might need to solve for that impedance based on what's given in your circuit. Our third step is to determine what value we want to correct the power factor to. So in this case, this was also given. In this case, we want our corrected power factor to be 0.95 lagging. Let's continue on to step 4. Our fourth step is to use the given equation to find x1. So in this case, the equation we want to use from our recipe is the following. x1 is r squared plus x squared divided by r times the tangent of inverse cosine of our corrected power factor minus x. So here we just need to substitute. R and x are both 100 in our circuit, so we have 100 squared plus 100 squared divided by 100 tangent of inverse cosine of 0.95 minus 100. So in this case, if we solve for x1, we get x1 is equal to negative 297.9 ohms. Don't worry that this is negative. We're actually going to see that the negative sign will cancel out and we'll end up with a positive capacitance. So in our final step, we use C equals -1 divided by omega x1 to determine the parallel capacitance needed. So in this case, we substitute and we determine that our capacitance C is just going to be -1 divided by, in this case, our omega C is going to be 377. Our x1 is minus 297.9. So we plug those in. 377 radians per second times negative 297.9 ohms. And you'll see if we plug that in, notice the negative signs cancel. And we'll determine the capacitance we need is approximately 8.9 times 10 to the -6 farads, or about 8.9 microfarads. So if we add that parallel capacitor, that will improve our power factor to be 0.95 lagging. Alright, so feel free to reach out if you have any questions on these examples. Let's now finish up with our last topic for today, which is maximum power transfer. So you may remember from our Lecture 8 video, where we first discussed maximum power transfer for DC circuits. And we learned in Lecture 8 that for DC circuits, the maximum power transfer theorem says that maximum power transfer happens when the load resistance equals the source's Thevenin resistance. And so we saw that in order to maximize the transfer between a source and a load, for DC circuits, load resistance needed to equal the source's Thevenin resistance. And we also learned that if maximum power transfer conditions were met, then we could calculate the maximum power we would be able to transfer. So this was the case for DC circuits. Let's see what happens in AC circuits. So it turns out in AC circuits, maximum power transfer theorem is very similar. In AC circuits, we will transfer the maximum average power, remember that's the real power P. The maximum average power is transferred when our load impedance is equal to the complex conjugate of the source's Thevenin impedance. So don't forget the complex conjugate. You'll see that complex conjugate is important here because it will actually enable the imaginary parts to cancel out and the result will be completely real. We can also show that if maximum power is met, so if Z load is equal to Z Thevenin star, then the maximum power that will be transferred is given by this equation. So notice that there's a slight difference in verbiage here because we're talking average power. Remember, average power is the real part of complex power. That's the letter P. That's the stuff we can actually use. So our goal here is to transfer the maximum possible P. So notice in this case, we can predict what the maximum possible p-value will be if we use this equation. Notice in the numerator we have the magnitude of the source's Thevenin voltage phasor squared divided by RTH, which is the real part of our Thevenin impedance. So there's a lot of similarity here between DC circuit maximum power transfer and AC circuit maximum power transfer. In both of these cases, it's very important that we know how to calculate the Thevenin equivalent of our circuit. So definitely, as you start preparing for our final exam, make sure you remember how to calculate Thevenin equivalent for DC and AC circuits. It's very important to know how to do this in order to find our maximum power transfer conditions. Let's finish with one last example for today. So here we have a circuit, and we are given that we have a 400 ohm resistor, a 0.8 Henry inductor, and our source voltage is 5 cosine 1000 t volts. And notice our load is not known yet, but we have basically our source on the left-hand side and the load part of our circuit on the right. First part of the question asks to find the impedance of the load so that maximum average power will be transferred. Next part asks what will be the maximum average power we're able to deliver. And in the last part, we are told to assume that the load contains a resistor in series with either an inductor or a capacitor. And if we assume maximum power conditions are met, we are asked to determine what components does the load contain. So let's go through this step by step. If you'd like, you can pause the video and try it yourself first. Okay, so let's begin with converting everyone to frequency domain. So in this case, if I take our circuit, convert to frequency domain, notice I still have my source, and then I'll just put my load on the right-hand side. We don't know what Z load is just yet. We know our source, this impedance of our source, will just be equal to our resistance, which is 400 ohms, plus j omega L to give us the impedance of our inductor. L is 0.8 henries, so therefore the impedance of our source is just 400 plus j 800 ohms. And we know our voltage, so in this case we can say our source is 5 angle 0 volts. Alright, so now that we're in frequency domain, let's start with part A. So in this case, we're asking ourselves, determine Z load so that the maximum average power will be transferred. From the source to the load. If you see a question like this on the homework or on an exam, you should be immediately happy, because you should immediately know what equation you need to use. Remember, for maximum power transfer, we must have our load impedance being equal to the complex conjugate of our source's Thevenin impedance. So in this case, notice we need to take complex conjugate of 400 plus J800. To take complex conjugate, we just flip the sign of the negative part. So we get 400 minus J800. So therefore, Z load must be 400 minus J800 ohms. Definitely make sure you write down that maximum power transfer theorem. It's a really useful and important equation. Let's move on to the next part now. Part B, we want to find the maximum average power that will be transferred. So in this case, we're going to go ahead and assume that maximum power transfer conditions are met. And we know from our equations and maximum power transfer theorem, we know that we can use this equation, 1/8 times the magnitude of our Thevenin voltage phasor squared divided by the real part of our Thevenin impedance. So we just have to substitute everybody in, and we get 1/8 times, notice here, the magnitude of our Thevenin voltage is, in this case, just 5. So 1/8 times 5 squared divided by the real part of our Thevenin impedance of our source. Well, the real part is just 400 from our 400 ohm resistor. So we plug in 400 down below. So we get 25 divided by 8 times 400, and therefore we determine the maximum average power we will be able to transfer is 0.0078125 watts, or about 7.8 milliwatts. Now let's finish with the last part. We want to identify the load if the load must be a resistor in series with a capacitor or inductor. So in this case, again, we're assuming maximum power transfer conditions are met, so we know that our Z load must be equal to our previous value, which was 400 minus J800 ohms. So notice that if we had a resistor and an inductor, Z load would be R plus J omega L. If we had a resistor and a capacitor, remember capacitor is 1 over J omega C. If we had resistor plus capacitor, we would have Z load being equal to our resistance R minus J times 1 over omega C. So in this case, notice that because our load has a negative imaginary part, it must contain a capacitor. Remember, the inductor will only generate a positive imaginary part. So in this case, we can determine, by comparing coefficients, we can say Z load equals 400 minus J 800. So in this case, our resistance is 400 ohms, and 1 over omega C must equal 800. In this case, omega is 1000, so we can say 1 over 1000 C equals 800, and therefore our capacitance must be 1.25 times 10 to the minus 6 farads. So therefore, in order to satisfy these requirements, we would need to have a 400 ohm resistor and a 1.25 times 10 to the minus 6 farad capacitor in series as our load. All right, so let's go ahead and wrap up here for today. You should now have a greater understanding of the physical significance of complex power and the power factor. Please make sure you've added all those equations to your toolbox so that you have them handy for our homework. Also, make sure you understand how the power factor can be used in order to efficiently transfer power to a load. Remember, most of the time we want our power factor to be as close as possible to 1 in order to maximize the real power that we're able to get. And finally, definitely make sure you add the maximum power transfer theorem to your toolbox. And make sure you know how to use those equations that we've covered. It's a very convenient final exam question to ask about maximum power transfer in AC circuits, because you also need to know about the Thevenin equivalent and frequency domain. So make sure you keep that equation handy. Thanks everyone for joining the fun, and I hope you found this video helpful. Thanks everyone, and we'll see you in the next video.